Thanks, Anastasia. Maybe I could kick off with a question of my own, and while others maybe can join. Okay. Well, the first question is a general one relative to the viscoelastic part. I mean, it's quite surprising if you think about it, that there's such a wealth of papers on 3D printed metamaterial, which totally ignore the issue of viscoelasticity. So, I mean, what should we do with that type of study? Should we consider it irrelevant? Should we take it? Should we conclude that there is a limited amount of these structures are not very verifiable, or are there ways that we could use in modeling to improve the way that we can predict their behavior? What is the way forward in this topic? That's the first question. The second question may be relative to the insect wings, the artificial wings. Did you verify if the patterns that you obtained reproduce patterns in nature, in actual insects?
Okay, yeah, clear. So I start answering from the first question. And indeed, there is a lot of literature reporting 3D printed polymeric structures. And some of them consider the viscoelasticity of materials by using simple or more advanced models. The others ignore it. But in overall, the goal depends on what we want to do. If the goal is to show experimentally the presence, for example, of wave attenuation mechanism, if the material attenuates waves, fine. However, if we want to model and to reproduce the experimentally measured behavior, then there are indeed problems. And to be honest, I have not seen any work. If you know, or anyone in the audience, please suggest me the model which reproduces accurately the viscoelastic response of 3D printed polymers. I was not able to find it. And based on that, I think that material properties of 3D printed polymers should be studied in more detail, because there are so many parameters there, starting from the direction of printing, then the printing technique, the quality of the material, even the initial powder size of 3D printed material matters for the final functionality. And there is not much research on this field. So we really need to do this research to be able to model the dynamic response of phononic, 3D printed phononics more accurately. And maybe if we can model it more accurately, we can find some other more exciting effects. So I hope this answers your first question. And if not, let me know. And for the second question, we try to reproduce the bi-inspired patterns by simply translating the structural design to the a design of an artificial 3D printed wing. We also see some effects, but it's very difficult to derive conclusions how that pattern influences the material dynamics, because natural patterns are described by a huge number of geometric parameters, and it's very difficult to understand which parameters are more important as compared to the others. So that's why, starting from the nature-inspired patterns, we thought, okay, if it does not work, if it is too complicated for us now, we switch to metamaterial patterns, which is, in the case of honeycomb structure, has just 5 geometric parameters, and explore that 5-dimensional design space. And in that space, we were able to find 2 important parameters, which are more important as compared to other 3. And by playing with them, to control a little bit the aerodynamic and the acoustic properties of the beam. But of course, there are much more patterns available than we analyzed. And I'm sure that by using more advanced optimization strategies as compared to our simple search in that low dimensional parameter space, they can deliver better results.
Okay, thanks very much for that, for those replies. Any other questions?
Good.
Yeah, yes.
Sorry.
This is Fernando. Can you hear me?
Yes, we can hear you. Go ahead with your question.
Okay. So first, congratulations to Anastasiia for this nice presentation, this very complete work with all the aspects have been tackled and faced. And so I want to confirm that, I would like to confirm that it is really important to test the properties of 3D printed polymers. And I have some experience with TPU, some initial experience with TPU, the same material that you have used, Anastasiia. And my experience is that this the response is indeed, as you have modeled, is indeed rate dependent. And there is also another important feature to point out is that usually these polymers are sensitive to preconditioning, and in the initial cycles they exhibit permanent strains that then are not shown in the subsequent history or loading history. And so one important result that I noticed with TPU is that if you pre-stress the sample, you basically you avoid these initial permanent strains, which can affect the response of the material in the first cycle. So if you pre-stress a little bit the material, you will get rid of this initial permanent strain effect. But I agree with you that this is a very open area of research, that the response of thermoplastic polymers, especially of TPU, which is in between a rubber and a thermoplastic material. So it's very important to model, to run experiments, to model through this the experimental behavior through effective models, as you have mentioned in the first part of your talk.
Yes, thank you, Fernando. Yeah, I didn't know that it's possible to eliminate this dependence by pre-stressing the material, but it can indeed be very interesting, because when you pre-stress, you increase the elastic modulus of the material, and this indeed will change the full behavior of this module, depending on the temperature, depending also on strain rate. And it would be interesting to characterize it, considering that current low-cost manufacturing techniques, they allowed quite good quality of 3D printed parts. As for example, for the beans, which I showed, we used a very simple printer. This is the filament diffusion technique, and the materials have also, the printed parts have some imperfections, but still, then we did the dynamic analysis. The agreement with the simulation result was accurate up to the second digit after the point. So we did not expect that, and it was quite surprising. So having currently available, commercially available manufacturing techniques really can simplifies the analysis and the material characterization, considering that also TPU can be printed by using the selective laser sintering technique, which implies much better microstructural characteristics of the 3D printed material. Yeah.
Yeah.
Regarding the effective properties, Do you know any results for this periodic viscoelastic metamaterials? You know,
no.
No?
No, I do not know for effective properties, no. But for me, you know, these mechanical models that I used, like generalized Maxwell model, it's already a kind of effective property because we try to put in one model in a couple of parameters all that complex material behavior that is dependent on the temperature, strain rate, on everything, and we try to reflect it just by a couple of coefficients. So to me, these models, they represent a kind of effective behavior, but I have not seen anything in terms of like truly homogenization of these materials. So I think this would be interesting research direction.
Yeah, if I can add another consideration is that maybe what is important is the angle between the loading direction and the direction of printing, of building the sample. So I think that's important because my feeling is that this material will be, the 3D printed material will be anisotropic, not isotropic. So I think this angle between the loading direction and the building directions, the position direction of the material would be important.
Yeah, it's definitely important because then you print structure which is longer than 10 centimeters. The variation in properties of the material is very different starting from the material density, because the initial part of the structure, which is located, so let me now come back to that schematics of the printing technique. So this will be more understandable, I guess. So it's here. Yeah, so what I mean is that the lowest part of the structure here will have higher density as compared, material density, as compared to the top part of the structure, because the higher is the taller or the larger is the structure along the printing direction, the lower is density, and the difference can be crucial, especially if we want to have highly loaded structures. So I had a collaborative project with University of Delft and one Swiss university, and they 3D printed a metallic structure, which was quite lengthy in this direction. And until they changed the printing direction, they always had failure modes during the initial excitation cycle. And then we realized that this is due to the difference in the material properties, and then they had to print the structure in the rotated direction to get rid of that dependence on the material density. And if the material density is varying, then of course the mechanical response will be different too. And the viscoelastic properties, and this will be not only the printing direction, but overall behavior in terms of mechanical properties will be very different too.
Yeah.
Hello, thank you very much for your interesting talk. It was great. I really loved it, especially the part about the viscoelastic part. I have a couple of questions with regards to that, like the Maxwell model that you used. It was unclear to me how many parameters, how many Maxwell terms you used for that generalized Maxwell element. And also, my understanding was that you were fitting a couple of parameters over your master curves. Mm-hmm. So the other question is, what was the frequency range that you were fitting these prony terms, basically? So were you interested in the entire frequency range, or like the narrow band that you were exciting your metamaterials with? Yeah.
Okay, I see. the number of terms in Maxwell, in the generalized Maxwell model, can be really very different. And in this work, then analyzed the behavior of viscoelastic, epoxy, and rubber. The Maxwell model was also fitting experimentally measured data, but these data were taken from other works, so I have nothing to do with those measurements. And for epoxy, it was 17 parameters model, if I remember correctly, so around that number. For rubber, it was 20 something elements, but it's not very critical, because the idea is that we need to have a good fit in the required frequency range, and more or less good agreement in the glassy and rubbery ranges. So here, these are these numbers. In the work there, we measured properties. So let me go quickly to that part. So this is for PMMA material. Here, if I remember correctly, there was also something around 15 terms. And we fitted the data in the frequency range which was measured. So this frequency range, plus 2 additional terms that represented the behavior in the rubbery zone and in the glassy zone, which were obtained from other experiments. So not a dynamic temperature superposition, but we had to also match the limits. So this is how it worked.
So you mean like another spring, which is like in parallel to your Maxwell model? Is that what you mean with regards to the rubber or glassy regime? Like
yes,
the
that was yes, indeed. One spring that represents the behavior in the rubbery region, and another, and the overall sum of the coefficients of the storage modulus coefficient should be equal to the value in the at the high frequencies, which was measured by time of flight experiments at very high frequency.
I see. So another question is that, does this increase in like the Maxwell terms that you use affect your computational cost a lot, or no, it doesn't matter that much how many Maxwell terms you use in terms of like how long your simulation will take, basically?
Yeah, I understand. No, it does not depend on the number of terms. You can use 3 terms, you can use 25 terms. But since you activate the viscoelastic behavior in COMSOL, and you specify that this is the Maxwell model, the simulation time increases enormously. And it does not depend on the number of coefficients. Yeah,
I see. So also with the for this shifting, have you used a specific program, or have you been looking at a specific other WLF or Arrhenius or any specific function, or you were basically looking at how good visually they are matching? Because I've seen different methods. I think TA Instruments, they have one rheometry program. It is not the Trias, but something else. And they are using like, you can basically change the location of that curves that you're shifting. And based on that, you can get like a better fit, but it's like all eyeballing, each of those, separate curves. Because you mentioned this Arrhenius fit here, I was like curious whether you use this function for shifting all your ISO temperature curves, or whether you were just, just shifting them to make sure that they look good, and then you fit whatever you get from your shifting factors, an Arrhenius function on it.
Okay. Yes. Yeah. So first of all, before doing the shift, we read the literature related to this material, so to PMMA and epoxy, and identify the most possible fits that were working nicely for other researchers. Then we had our measurement data, and if I remember correctly, because it was not me who did these measurements, but my Italian colleagues, they used the program which is a part of rheological instrument for these measurements. But after they obtained that more or less good visual shift, but not only visual, they also estimate the quality of the shift by calculating some coefficients, and they calculate the activation energy. And the activation energy value should be meaningful. And this is exactly the reason why for epoxy case, so let me open it. Here, the activation energy was not meaningful. Even the fit was not that bad, let's say, okay, except some deviations, but the activation energy did not correspond to the one reported experimentally. So that was the quality of a bad fit, in addition to not nicely looking curves.
I see. Sorry to interrupt you. While I'm looking at this is loss curves and your tan delta, I can see that for each of those, you know, ISO temperature curves, you have a lot of frequency terms. Mostly the match is not really good for your higher frequency values, as I can see there, but for your low frequency values, so I'm not sure what was like the table, like the discrete values of frequency that you tried at each temperature. But based on what I can see in this graph, if you decrease the number of frequency, those discrete frequencies from like whatever it is, like it's like 0.5 hertz. So let's say, I'm not sure if what that is, like 100 hertz or 200 hertz, if whatever the device is capable of measuring. But if you basically from 0.5 hertz go to like 10 hertz and try to match the loss modulus or tan delta, I could see that there should be a better fit. Again, I'm not sure, but I can only see that the higher frequency values are kind of off. And the other thing that just like, you know, occurred to me right now is all your shifts are based on the storage modulus. So you haven't shifted like based on the loss modulus or the tan delta or the average value. Yeah.
Yes. This is an example. We did all kinds of shifts, and other shifts can be found in the supplementary material of that paper. So we did the shifts on the storage modulus, also on averaged values. It just does not work. And actually the impression that you got by looking at this data, it's because these are already clean data. They do not contain high frequency content. So this is already low frequency.
So it's like
because with high frequency, it's a mess. It's total mess. So just you know, to visualize it and to show what are the trends, they kept only the low frequency content. Maybe they could reduce it further, but here the idea was to illustrate that even by preserving nice, let's say, values, we cannot obtain a good master curve. And yes, you're right. Here is a shift for storage modulus, but we did the other shifts too, and yeah, we got the same messy curves.
I see. So you believe, so my last question, sorry that it takes a lot of time, and I think we're running out of time. So my last question is, not even like with trying with higher number of Maxwell terms, you could have not matched the experiments with your Maxwell model really like greatly, right? Okay.
No.
Okay, I see. Thank you very much.
Thank you for your questions.
Thank you.
Thank you.
I think Nicolas Pugnot has a question.
Okay, and sorry, I'm driving, but compliments Anastasia for your presentation. I have just a very simple comment and a question. One comment is this: you mentioned that in nature you don't see real periodic structure, and I'm wondering, perhaps I'm suspecting that this is just because the perfectly periodic structure is simply not the best one. And then in this period, I have a general, perhaps two general comments. You discussed some application in metamaterials, and do you see any application regarding peace? Thank you.
Regarding what?
Peace, to maintaining peace, not war or defense. They are the classical application, but peace.
Peace? No, unfortunately. Yeah, would be really nice, but I do not see it for now.
So Nicolas was mentioning that periodic might not be ideal. So what about quasi-periodic?
Yeah, that can be really nice. And for that, we need a more elaborate technique. because indeed, if we consider the patterns of natural winds, so let me move to it quickly. They are highly non-periodic, and to a certain extent, they can be considered as quasi-periodic. So here it is, because you can see that, you know, they have more or less equal areas separated by winds, and they are all elongated along the chord direction of the wind. So it would be really nice to consider them. And even more, there are researchers who use the machine learning technique to study the arrangement of these winds and their influence on the flight dynamics, and they of course found that it has a great influence. Now we cannot do it. I mean, we cannot analyze non-periodic designs in our group because we do not have, first, powerful technique that allows to consider such large number of parameters, and second, to have sufficient computational time. Because for analysis of a single pattern in this simplified setting that we have, and simplified in the sense that we do not consider the angle of attack, we do not consider the influence of wind, that will be the case if we analyze forward flights, for example, that increases the dimensions of the parameter space. So a single simulation in this setting took 5 hours on very powerful cluster in Switzerland. And, you know, the fact that we were able to analyze 1,000 of cases, it took several months of calculations. And we were quite happy that it delivered some more or less optimized results. So something should be done maybe from the computational point of view to consider some simplified but still reliable setting in which we can analyze the influence of patterns. However, personally, I do not believe that real simplification of the model is possible, because there are many works in this field and they try to consider 2D dynamics. They introduce different analytical techniques to describe interactions of the wind with the air. And almost all of them were proven to be insufficiently accurate in terms of the analysis of the pattern on the aerodynamics characteristics. So this should be indeed a full 3D fluid structure interaction analysis. And just the question how to run it and to go through the parameter space of quasi-periodic structures in an efficient way. So I think this is the biggest challenge here.
And okay, so you have yet another question. You know, you have a phase transition between periodic and random, and so so how do you think going from, well, let's say almost periodic to random will, you know, random might lead to something which is almost amorphous phase. So how will it affect the band diagrams? When do you lose actually the band structure? At which point do you lose the band structure? You know, how much randomization do you need to bring into the system so that you cannot even trust any block diagram? Because here, clearly, effectively, it's more like a graded metamaterial. Effectively, like you said, it's not really a periodic pattern. The green one. So how much can you trust the periodic approximation?
Okay, I understand. Here I do not analyze any band diagrams. Yeah.
Okay,
so
not at all.
Not at all, because
okay.
What we do, let me go to the description of the model. So we consider a wind which does this flapping type of motions in air. And air is modeled as an ellipse.
Okay.
Air is described by viscous incompressible Navier-Stokes equations. And this approximation is fully valid if we consider low Reynolds number flights. So this is no approximation here introduced. And then we consider equations of motion for the wind, which assume to be compressible, elastic as it is, and it undergoes large deformations. So we write down the formulation for large deformations regimes.
Okay.
And then we consider only how the pattern that we have at the surface of the wind influences the sound and pressure field in the surrounding air.
Mm-hmm.
And for that, we construct two functionals. One is the lift functional. So basically, we consider the difference between the pressure at the top of the ellipse as compared to that at the bottom. And from that, we calculate the lift. And in the same way, we estimate the generated sound by analyzing the pressure at the top surface of the ellipse. So we do not consider, and by changing the structure, so for example, we change a parameter like this, we consider how these changes on the surface of the wind influence the values of the lift and sound functionals. And based on that, derive conclusions on can we increase them or decrease, and how we can control which parameters are more important as compared to the others.
But you don't make use at all of the fact that it's a, well, quasi-periodic structure. You don't have this at all. I mean, because, you know.
Yes, I understand what you mean. So first of all,
I
do not.
Yeah, in your model, actually, it could be any kind of structure inside. You don't use at all the fact that you have a specific geometry to reduce the computational time.
No, I do, because my specific geometry is described by a few geometric parameters. Yeah, and it's also possible to cover the full surface of the wind by the pattern, but we do not do it. Why? Because we have these bounding vanes which allow to preserve the structural rigidity. So basically, these parts in the thinnest parts of the wind, they have just one printed layer, and if it goes up to the end, the dynamics will be really not stable. So that's why we preserve the external vane, we call it like that, just to increase the structural rigidity at the edges. And then in the interior of the wind on the surface, we apply this still periodic pattern. So it's not quasi-periodic, it's fully periodic. And in this case, it is described by 5 parameters. So this is the thickness, the elongation factor, so basically anisotropy along the chord and span-wise directions. And also the thickness, out of plane thickness, and okay, maybe 4, because 5 it's in another study which is currently under review. There we also try to analyze the auxetic patterns on it. And then by changing these parameters, we
so
try
you look also in negative Poisson ratio. You looked at
yes, we looked at it. I do not report these results here, but we looked at it too. It's currently under review. Yes.
I mean, 5 has some kind of auxetic features.
Yes, if we also change the inclination angle here, so that this elements go become like auxetic structure, then we can also cover the range of auxetic lattices.
Okay.
Yeah. And it appears that some parameters are less relevant, so we can ignore them. And we do it not by running the optimization study in the classic sense, then we say that we want to optimize lift, but we do it by constructing these maps, which suggest us the influence of the interdependencies between the parameters. So here you can see, for example, that then the scale parameter along one of the axes is larger than 0.9. There is no effect. There is no dependence basically between this parameter and the parameter of the height of the thickness of that element. So that means that the optimal designs are located in this region. And then we try to use these maps to find some optimized designs in terms of our targets.
Yeah. In terms of the nonlinearity, would you say that it's so you speak of elasticity of large deformation? I mean, it's okay. It's so it's elastoplasticity, or it remains. I mean, what is theoretical?
No, it remains elastic. There are no plastic effects, and we also do not observe any plasticity in experiments.
Okay. And again, you cannot point to some work that might, have, I mean, your work might trigger some interest in, homogenization analysis, because you might first, kind of analyze the periodic or quasi-periodic structure and then replace this by some kind of effective structures that would have same kind of behavior to help your optimization algorithm. Because when you talk about 5 hours per computation and you said that it's on a supercomputer in Switzerland, and then you have to run 1,000, I mean, it's amazing the cost.
Yes, but even having a periodic pattern, as you can see here, then the distribution of stresses in the structure is non-uniform.
Yeah.
So, and the velocity fields in the surrounding air are also non-uniform. So I'm not a specialist in homogenization, but really I do not know how it can be applied here, because the deflections from the equilibrium positions, they are they are quite large. This results in non-uniform fields. Even for periodic design. And now if we assume non-periodic arrangement or even arbitrary, then it becomes a disaster.
Okay. I mean, this is really inspiring. This is really great. So apart from these dragonflies, what kind of other, I mean, butterflies have similar, morpho-butterflies have similar structures, or not at all?
Yes, they also have flexible, very lightweight wings, and also the results I showed to you, they were also reported to the biomimetics group here in the University of Groningen, and they say that the similar analysis technique can be applied to the wings of birds, which have absolutely different dynamics. And again, here, for insect wings, for bird wings, we can benefit to control the flight conditions from very different dynamics of the wings, because these wings, they can deploy, they can fold, they can rotate, they can flap, for bird wings. And all these different flight conditions, they result in different aerodynamic and also acoustic properties. Because if we consider the patterns of natural dragonfly wings here, and there are studies which analyze the patterns in natural flyers, and they say that the pattern first is different for per gender. So different genders, they have different patterning system, and they also are different from species. Of course, every pattern is individual because these are biological structures, but still they have some similarities, and the arrangement of pattern is responsible for the generated sound. And insects use this sound for communication purposes. For example, they can transfer the information about the danger, or for sexual purposes also, because different genders generate different sounds, and in this way they attract or distract each other by using the same territory. So that's why the idea of patterning is really promising also for artificial flying robots, because by applying different patterns, we can control the sound of these robots, and we can make it different depending on the purposes. So for certain purposes, we can try to aim at silent, let's say, flying vehicles with minimum generated sound. For other purposes, we can make the sound very specific, so these devices become recognizable. And that was the inspiration for this study, and we still look into different possibilities to continue this study and to analyze not only different pattern types, but also how they can be introduced in the structure, because the current the current way we used it, just let's say preliminary study, the very first idea that we got, and it implies applying the pattern on the top of a homogeneous wing. But in nature, they are constructed differently. The pattern goes through the whole wing. This is also influences the wind dynamics because the lift is generated by the pressure difference from the top and from the bottom. And this will be another interesting direction. What's going on if the pattern goes through the full wing, and how can we benefit from having it? How can we use it not only for flight dynamics, because it's already quite advanced and promising for many applications, but also to control some, let's say, secondary characteristics, like, for example, generated sound.
And I have a last question. It's a bit crazy, so you can just say, this is stupid, and this, I mean, not to ask it, but what is there any connection with time modulated metamaterials? I mean, I understand it's a but could you relate this to some kind of space-time?
Sebastian, I need to think about. I do not know much about time modulated metamaterials. Probably there is, but I really need to have a look at that field.
And very finally, could you speak again about this curvature? The curvature, is it a very small, weak curvature, because it looks quite curved?
Yeah, it's quite curved. We were not able to print it by means of a single nozzle printer. It really requires a support and structure to be printed properly. In Switzerland, they had a smaller bachelor project trying to print these wings by a standard printer without a supporting material. And due to the curvature, it was not possible, regardless of the printing direction. So what we did, they printed the support from top, and then the wing was, let's say, lying on that support. And then we washed the support because it was alcohol-based supporting material that can be removed quite easily.
Okay, look, Anastasiia, I have finished with my question. I just wanted to mention that, I mean, this is absolutely amazing work. I mean, I'm totally amazed.
Thank you very much. Thank you, Sebastian.
Now I leave Mr. Chairman with other candidates for questions. Federico, the field is yours.
Okay, well, I guess we can bring this to a close. Thanks very much, Anastasiia. As Sebastian was saying, this was a great talk, and it's always inspiring to hear you come up with different ideas and new directions for this field. So thanks very much. And I also thank Sebastian and Bogdan for this series of seminars, which are always very interesting, and try to follow them every time I can. Thanks, everyone.
Thank you, Federica, and indeed, thank you, Sebastian, Bogdan, for inviting me. It was a pleasure to give this talk. Thank you.
Thank you, Anastasiia. Thank you all. And see you next week.
See you next week.
Yeah.
Bye.
Bye-bye.